Okay, so I'm having computer problems today. The account that I'm on right now is not my actual account. So it's a separate account I had to make like 20 minutes ago. So I can't actually show you. I don't actually have the Windows, the Linux subsystem for Windows on here. So I can't actually run any code today or show you the fixed version of the toString function from last day. So the toString is in fact broken. And the fact that it actually seemed to work in last class is just something that you have to realize happens in C. If you change the demo program a little bit, it actually breaks. So I have to, next class, I hope, I'll show you the fixed version of it. And I'll post it on the OnQ. So today, I want to move on. So we implemented a list using an array in the last class. I want to show you how to do something else. So eventually, I want to show you how to implement a list using, I want to show you how to implement what's called a linked list. So it's a linked series of nodes. But instead of jumping straight into a linked list, I'm going to back up one step and do something a little bit simpler. So I'm going to show you how to implement a stack using a bunch of linked nodes. If anybody in here happens to be in 124, you have almost the same lecture this morning. So by coincidence, the two courses lined up today. So just to quickly remind you, these are examples. These are real-life examples of stacks, right? Stack of papers, stack of books, stack of pancakes. In the data structure called a stack, there's the notion of the top of the stack, right? So here you've got a stack of books, right? The book on top is called the top element of the stack. In a data structure, you can only access the stack via the top element. Okay? So you can't reach into the middle of the stack and pull out the middle element, for example. Right? Everything happens at the top of the stack. Now, it's a very simple data structure. So classically, stacks only support two operations. There's the push operation, where you put something on top of the stack. And there's the pop operation, where you take the thing on the top of the stack off. Right? And that's it. Those are the only two operations that you can do with a classical stack. If you try to pop the empty stack, there's some sort of error should occur. Right? OK. So push. What does push look like? So if I push the number 1 onto this stack called ST, you end up with one element sitting here on the stack. Right? So that's a stack of size 1. And you've got this thing called top that points to the top element of the stack. Right? If you push a 2 onto ST, 2 now appears on top of the stack, right? And top now points to the second element on the stack. Right? And so on, and so on, and so on. Right? So there's your stack, stack of size 5, right? With your elements 1 through 5 on the stack. Right? Now, if you look at the stack, you can see that the elements in the stack, right, they are in the order where you put them on the stack. Right? But they're in the reverse order. So if you start taking them out, the last element that you put in is the first one that comes out. Right? So when you start to pop elements from the stack, right, x is now the value. So right, if I pop that stack, x becomes the value 5. Right? So the element that's on top of the stack gets returned by pop, and the value gets stored in x. Right? And then that element disappears. Right? And the top of the stack now points at the 4. Right? Same thing. Right? Then the 3, then the 2, and then the 1. Right? So the stack, the order the elements come out is the opposite of the orders that they went in. Right? So a stack's called a, do I tell you this? No, I don't tell you this. It's called a LIFO, L-I-F-O data structure. Last in, first out. OK, now these things are used quite a lot in computer science and computer engineering. So if you ever use undo or redo on your application, whatever application on your computer, right, that's almost certainly implemented using a pair of stacks. Right? So the way that works is every time you do something in your application, right, you perform some command, right, whether it's typing in your word processor or highlighting something and deleting it, right, copying and pasting, right, a version of that command gets pushed onto a stack. Right? If you go to undo the command, what happens is you pop the stack, the undo stack, you look at the command, you undo the command. Right? If you also have redo, then that command you just undid gets pushed onto the redo stack. Right? So then if you hit redo, right? It pops the redo stack, looks at the command that's there, undoes the command. Right? So that's how undo redo is normally implemented in your desktop or whatever your application you're using. They're widely used in parsing. So parsing is when you have a program that has to read some text of some kind. Right? So for example, your compiler has to parse your C program. Right? So stacks are widely used in parsing. The way most C implementations work is that there's something called the call stack. So the call stack is used to store information about any functions that are active in your C program. Right? So every time you call a function, a version of that function gets pushed onto a stack somewhere. Right? If that function calls another function, that other function gets pushed on top of the stack. Right? When that function finishes, it gets popped off the stack, and then control flow goes back to the next element on the stack, and so on and so forth. Now, you can emulate that call stack. So that's actually the C runtime, right? So you don't have any control over it. But you can emulate that call stack yourself by using a stack. Right? And so you can convert a recursive function into a non-recursive one by using a stack. Right? So when you take CISC235 or CISC365, you'll see algorithms that usually work on trees or graphs that use a stack to implement an iterative version of an algorithm instead of a recursive version of an algorithm. OK, here's a silly example of using a stack. So you should not do this, right? But this will show you an example of using a stack. So I'm going to use a stack to reverse an array. Right? So you have an array. I want to reverse the order of the elements in the array. Right? One way to do this is using a stack. So here's a function that will do it. Right? Notice the title. Right? So don't do this. Right? So I'm going to reverse an array having n elements in the array. Right? I'm going to do it by making a stack. So the class, not the class, the type that we're going to implement today is called lStack for a linked stack. Right? So I'm going to make a stack, and then I'm going to loop over the elements in that array. Right? So for I equals 0, I is less than n, I'm just going to push every element of that array onto this stack. Right? When I'm done with all the elements in the array, I'm then going to go back to the stack, and now I'm going to pop all the elements onto the stack. Right? Each time I pop the stack, I'm going to store the element into array I. Right? So the first time this loop runs, the first element of the array will be the first thing popped off the stack. Right? The first thing popped off the stack was the last element in the array. Right? And then, of course, you should free the stack because you're done with the stack. Right? So this is what happens in a picture. There's my array, right? 1, 2, 3. I've got an empty stack. Right? I'm going to iterate over the array and push the elements onto the stack. Right? So 1's going to go on the stack. Right? Then 2 is going to go on the stack. 3 is going to go on the stack. Right? Notice I'm not removing things from the array. Right? Now that I'm done with the array, I'm now going to pop the stack until it's empty. Right? So starting with 3, I'm going to move that. I'm going to pop the 3 and store the popped element into the first element of the array. Right? And then, so there goes the top element. Right? Next element, the 2. Oh, wait, that's a typo. The 2 goes into the, I'm going to pop the 2, so I'm going to put it into the second element in the array. So there it goes. Right? And then hopefully I fixed the next one. There we go. Right? And now the 1, I'm going to copy that into the third element of the array, and I'm going to pop that. Right? So now you've got an empty stack. And your array has been reversed. Right? So that's an example of exploiting the last in, first out structure of a stack. OK, so you shouldn't do that. So the reason you shouldn't do that is because you can reverse the array without using any extra memory. Right? To reverse using a stack, you need a stack of size n, right? Where n is the number of elements in the array. Right? So don't do it this way. Just write a loop and reverse the elements of the array directly. All right. Now, you can easily implement a stack using an array or using the list that we implemented in the last class. Right? So to implement a stack using an array or list, every time you push something onto the stack, you just set the last element that's free in the array. Right? Or you add something to the end of the list. Right? Every time you pop, you remove the last element of the list, or you return the last element that you set in the array. Right? So it's actually very easy to implement with an array or an array list. The problem is the push operation. Right? So if you have an array of capacity 5, right, then you can only push 5 things onto that stack. Right? When you want to push the 6th element on the stack, you have to do something to the array. Right? So you have to increase its capacity somehow. Right? To increase its capacity, you have to copy all the elements that are in the array. So that every once in a while, push becomes big O of n. Right? Most of the time it's big O1 because most of the time there's room in the array. Every once in a while, when you resize the array, complexity becomes big O(n). Right? So you can guarantee a complexity of big O1 if you avoid using an array. Right? So that's what I want to show you how to do today. All right. So many data structures use something called a node. Right? So a data structure that represents a collection of elements. A lot of them, well, the ones here are typically implemented using nodes. Right? So a linked list is implemented using nodes. You might have seen them in 124. You will probably see them in CISC235, right, the data structures course. You'll definitely see trees in CISC235. And then graphs you may see in CISC235. You'll definitely see them in CISC365. If you take Math 401, which is the graph theory course, you'll see them again. Right? Math 401 is the theoretical treatment of graphs. OK, so how do these things work? Well, you've got this thing called a node. And inside of a node, right, every node stores an element. Right? So if it's an int or a double or something like that, you can store an element, right, in the node. If it's something more complicated, you can store a pointer to an element. Right? We're not going to do that today. That's a little bit more complicated than I want to get into. It's not a lot more, but it's a little bit more. So right now, today, I want to use nodes where they directly store an element. Right? Now, in general, a node also has pointers to 0 or more other nodes. Right? So you've got a structure called node. Inside that structure is a pointer to 0 or more other nodes. Right? And these pointers are called links. So for a stack is just a linear collection of items, right? So the elements are arranged in some sequence, right? Starting from the top element, right, down to the bottom element. And every element is only connected to the next element that's deeper in the stack, right? So there's something on either side of each element, right? So that's why we call it a linear data structure. OK, so to implement a node for a stack, I need to be able to store the element, and then I need one pointer inside the node, right? So I need one pointer that points to the next node that's deeper in the stack, right? So in other words, that picture here, that's a node, right? So that whole thing there is a node. So the 1 inside the box, that's the element. The arrow, that's your pointer, right? So that's the pointer to the next node, right? If you only have one thing in the stack, there's no next node, right? There's no other element in the stack, so that pointer points to null, right? It points to nothing. Right? So there's your element. There's your link, right? Which is just a pointer. Right? When I push an element onto the stack, right? What do I need to do? Well, I need to make a new node, right? So I want to stick a node up here, right? And that node should hold the element that you're pushing onto the stack, right? So if I push the 2 onto the stack, I need to make a node, and I need to stick 2 into the node, right? But now I need to complete the link, right? So I need to make this node point to that node there, right? So I want to set the link of the new node to point to the current top node of the stack, right? So that top thing right there, right, that's a pointer to the current top element, right? So I want to make 2 point to the current top element, right? So there goes the link. Step 3, right? Well, I've just pushed something onto the stack, so that's now the top of the stack. So I want to make top refer to 2. Right? So I do that. Right? And then finally, what did I just do? Well, I just added one element to the stack, so the size of the stack increased by 1. Right? So I want to add 1 to the side of the stack. OK, so if I push another element onto the stack, I now want to look at pop. Right? So how do I pop an element off this stack? Right? OK. So when I pop the element, I want to return that 3 back to the caller, right? So I need to make a copy of that 3, right? So copy the element stored in the current top node, right? So I'm going to copy the 3, which is why I'm showing it in red, right? So somewhere you've got a little variable out here, right? X equals 3 or something like that. Right? I now want top to point to the next element in the stack, right? So set top to point to the next node deeper in the stack, right? So I want to do something like that. Now I want to get rid of this node, right? Now in C, you have to manually get rid of this node, right? Because I need to free the memory that's associated with that node, right? Right? So I have to do that operation there, right? So I need to free whatever memory was allocated to that node. Now I need to subtract 1 from the stack size, right? And then return the copy of that element that I got out of the node in step 1, right? So I need to return the 3. Okay, so let's look at the source code for this thing. Okay, so the header file first of all. So you can see I've got all these red underlines. That's because I don't have Linux installed on here, so I don't have a compiler on here either. So code thinks that this is an error. Right, so I'm going to include standard bool so that I can use the bool type. Right, now just like with our list, right, I'm going to declare an incomplete structure here. Right, so I'm going to declare a structure called lstack. Right, and I'm going to give that the name lstack, right, using a type def. Right, I've got a function here that makes a new stack and returns a pointer to the new stack. Right, I've got a function here that returns true if the stack is empty. Right, so if you pass in a stack s, if it's empty, it'll return true. Right, I've got a function here that returns the number of elements in a stack. Right, this one will push that element onto that stack. This function here will pop the element off of the stack and return the element that's stored in that was on the top of the stack. And now I have a function here that frees any memory allocated to the stack S. And instead of generating a string, today I'm just going to print the stack instead. Right, so you can put in the toString method if you want, function if you want to. Here I'm just going to print it directly. Right. Okay, so that's the header file for the stack class. Right. Now I need to implement all of these functions. So you're going to do that inside of your lstack.c. Right. Now inside here is where you see the node. Right. So anyone who's using this stack class, right, so notice that's their interface. Right. So you can imagine this to be a Java interface. So that's the programming interface that they're going to use when they use the stack. Right. There's no mention of a node anywhere in this header file. Right. So the user of the stack class never knows that there are nodes that are storing the elements. Right. Instead, right, that's an implementation detail that's stored inside of the stack.c source code file. Right. So there's my declaration of a node. Right. So this is an incomplete declaration as well. Right. So I've got a structure called a node. Right. I'm going to type def that to node, so I can just write node instead of struct node everywhere. Right. Now on the next few lines, I'm going to define the node. So what's in a node? Well, this is a node that can hold ints. Right. So I have my element. Right. And then, right, I've got a pointer to the next node. Right. Now, what you cannot do is you cannot do this. You can't do that. Right. The reason you can't do that is because, right, that's saying your node actually has another node object inside of it. Right. Which doesn't work because that node object must have another node object inside of it. Right? And that node object must have another node object inside of it. In other words, it's infinitely recursive. Right? So you can't say that a node has a node. Right? But what you can say is you can say a node has a pointer to a node. Right? So that's not infinitely recursive. Right? A node has a pointer to a node. Right? So that one's fine. Right? Okay, now what about my stack? So this is where I actually define the stack structure itself. Right? The stack has nothing in it, almost nothing in it. Right? I know the size of the stack, and I have a pointer to the top node, and that's it. Right? I don't have an array of all of the nodes in the stack. Right? All that I know is that all that I have is a pointer to the top node. Right? To get to any other node, I have to follow those next pointers, right? Those links to the other nodes. right? But you can see the stack structure itself is very compact, right? All it has is a pointer and size and the size of the number of nodes, right? Okay. How do I make an empty stack? Right? So to make an empty stack, right, I need to allocate space for the stack, right? So you're going to use malloc here, right? How much space do I need? Well, I need the size of a stack, right? That returns a pointer, right? If the pointer is null, then malloc failed, so I'm going to return null. Okay, now I need to initialize these two fields, or these two members of the structure. Right? So in an empty stack, right, there is no top node, right? So that's going to be null, right? And the size will be 0, right? And now you're done, right? Because there's only two members in the stack anyway. So you're done the initialization, so you go ahead and return S, right? And that will return back to the caller an empty stack, right? So in a demo, here's a demo program, right? So in the demo program, the first thing I'm going to do is make an empty stack. And then I'm going to try to print it out and push things onto it and pop things off of it and so on and so forth. Right? Okay. Anybody have any questions about the initialization function? All right. Is a stack empty? Okay, so notice I'm passing in a const stack here, right? So it's a pointer to a const stack. So in other words, I can't change the stack. Right? Well, the function promises not to change the state of the stack. Right? So anybody who's using this function knows that they can pass in a pointer to their stack, and they're guaranteed that their stack's not going to be changed. Right? How do I tell if a stack is empty? Well, if the size is 0, it's empty. So I can just get the size. Right? And remember, you're using the arrow operator to dereference the pointer. Right? Dereference the pointer and then access the member. Right? So is the size of if the size of the stack is 0, it's empty, right? Otherwise, return false. What's the size of a stack? Well, just dereference the pointer, right? And then access the size field or member. Right? What about push? Now, remember push here. So what does push look like? So push is going to look like, I need these 4 steps here, right? Make a new node. Okay, in C that's easy, right? You just use malloc, right? So I malloc a new node, or malloc space for a new node, right? If the node is null, right, return false to indicate that we couldn't push this element onto the stack, right? Okay, that's easy. Step 2, whoops, sorry. Where is it? Here. Step 2, set the link of the new node to point to the current top node, okay? I'm going to store the element in the node first, right? So put the element into the node. Now, what's the next link in the node? Well, that's supposed to point to the current top of the stack. What's the current top of the stack? Well, it's just S top, right? There you go. So that's step 2. Step 3, set top to refer to the new node. Okay, so what's top? Well, it's just S top, right? What's the new node? Well, it's just N, right? So S top equals N, right? I've just pushed something onto the stack, so its size increases by 1, right? And if you reach this point, right, you've got your node, right? I've put it onto the top of the stack here, right? I've increased the size of the stack, so everything's done. So now I can return true, right? Indicating that we successfully pushed something onto the stack. Now, what about pop? Right, so you just go back to the slide, popping. So I need these steps, sorry, here, right? So I want to copy the element stored in the current top node. Come on. There we go. Right. So I'm going to grab a pointer to the top element in the stack. So there's something else here that's missing here, right? So what's missing from that slide is that you have to manually deallocate that top node yourself, the old top node, right? So the first thing I'm going to do is I'm going to grab a pointer to that current top node, right? So I'm going to get a pointer to the top node so that I can free it down here, right? So that I can deallocate the memory that was allocated to that node. Right? If I don't deallocate that memory, right? Pop still works, but you end up with a memory leak, right? Every time you push something onto the stack and then pop it off, you don't release the memory to that node, right? So if you have a long-running program where you're, or if you push and pop many elements onto that stack, right, you'll eventually run out of memory, right? Okay, so grab a pointer to the top element, free it later, but otherwise everything's just as described in the slide, right? So I'm going to make a copy of the element stored in the node, right? Remember, what's the current node? The node is the top node, right? Next step. Set top to point to the next node deeper in the stack. Okay, so that's the cute part in this. So I want to set stop to point to the next node in the stack, right? The next node in the stack is top.next, right? It's also, if you wanted to write it this way, it's also that, right? It's also stop next, right? Because top is the current top of the stack, right? Because I haven't changed it yet, right? And I can get the, that's a node, right? So I can dereference that node and get its next link, right? So if you wanted to, you could write it like that as well, right? But I've already made a variable top here, so I'm just going to use that one. Right? So that now points, that next top now points to the next element in the stack, right? Decrease the size by 1, free the old top node, and return the element back to the caller. The one thing you have to wonder about is whether or not this is correct when the stack only has one element in it. Right? So when I, oops, sorry. I need to get a stack with one element. Okay, here. So if I pop that stack, right, and I set top to be equal to that node's next link, right, what do you end up setting top to? Well, you end up setting it to null, which is correct, right? So for an empty stack, the next node is null, right? So it turns out that slide is in fact, the code is in fact correct, sorry. Right? All right, anybody have any questions so far? Okay. How about freeing the stack? All right, now freeing the stack, so when someone calls free, right, there's no guarantee that they're freeing an empty stack, right? You can free a stack with 100 elements on it if you wanted to, right? But if you, in this function, if that's the case, right, not only do you have to free the memory that's allocated to the stack structure itself, you have to free all the memory that's allocated to all of the nodes in the stack, right? And so what you need to do is you need to iterate over all the nodes. Right? Now the problem we have here is that you don't have an array of nodes, right? You've got this linked structure, right? So how do you iterate over a linked sequence, right? So freeing the elements from a stack or printing the elements in the stack means that I have to iterate over all the elements, right? Over all the nodes, right? And it turns out that iterating over some sequence of nodes is a very common operation, right? So whenever you work with these linked structures, it turns out that many of the algorithms require iterating over some sequence of nodes. Right? For the stack class, you're iterating from the start to the end. Right? Okay, now at the end of the sequence, right, there's a node whose next link is null. Right? So that's how you know you've reached the end of the sequence. Right? When you reach a node whose next link is null, or when you reach a node that is null, you're done, right? You're done the iteration. So all you have to do is start at the first node of the sequence, and you just follow each next link, right, to the next node until you reach a null node. So the general iteration pattern for a linear linked structure looks as follows. Right? You make a pointer and assign the pointer to whatever starting node you want, right? So wherever you want to start the iteration, you set n to point to that node, right? Now, while n is not null, right, there's a node there. Right? So inside the loop now, I can do something with n, right? So I can dereference n safely, right? So I can dereference n, access its members, whatever I want to do with it, it's fine, right? So I can do whatever I want with n in here, right? And then you advance to the next node, right? So how do I advance to the next node? Well, I just say n equals n next, right? N next is the pointer to the next node, right? So if you assign that to n, that effectively moves you to the next node in the sequence, right? Then you come back up here to the loop condition, right? If n's not null, you go again, right? Whenever you hit a node n whose next link is null, right? The next iteration n will be equal to null, so the loop will stop. Now, what you have to remember is n is null after the loop, right? So whatever you do, don't dereference n here, right? So you have to be very careful not to dereference n there, right? Because if you do, bad things will happen, right? In C, it's undefined behavior. So your program might crash, it might not, right? Which really sucks when you go to debug, by the way. All right, so this is what it looks like in a picture. N's a pointer, right? So it's pointing to the top node of the stack, right? N's not null, so I can do something with this node, right? Next iteration, n is equal to n dot next, right? So n next. So that's n next, right? So n next, so now I point to the next node, right? Not null, so do something with the 2, right? Then go to n next, right? So follow the link, right? N's not null, so I can do something with the 1, right? Then I can go to n next, right? So that's null, right? So now I know I'm done, right? And so now you don't do anything with n, right? Okay, so let me go back to freeing the stack. Right? So all you do is you take that pattern and you just paste it in here, right? So my pointer to a node starts at the top of the stack, right? While n, right? So while n's not null, right? Do something with n, right? Okay, so what am I going to do with n? So I'm going to free n, right? But before I free n, right, I need to remember what the next link is, right? If you free n before doing this line, right, you can't safely use n to get to n next, right? So I need to remember, I need a little variable here, a little temporary variable to remember what is the next link. What node does the next link point to, right? Then I can go ahead and free n, and then I can say n equals next. Right, so that's the one little change on this slide compared to the general pattern. Right? Here, because I'm actually freeing the node, I can't use n equals n next here. Right? So I need a temporary variable. Right? So what's that going to do? That's going to iterate over the nodes. Every time you get to a node, you free the node. Right? And that releases the memory that's associated with the node. When I get to the end, so after I freed the last node, I can now free the memory associated with the stack itself. Right? So in other words, I can free the memory for the pointer and for the holding the size. Okay, now what about printing? So suppose I want to print a stack, right? So printing a stack is the same thing as iterating over the nodes, right? So if I iterate over the stack S, right, I'm going to print out top, comma, and then I'm going to print out all the elements. Right, so all the elements starting from the top element, going down to the bottom, comma, and then print bottom. Right, so this will print something like top, comma 3, comma 2, comma 1, comma bottom. Right, so that's an example of a string that this will print out. Right. Well, I have to iterate over the nodes. Right, so you take the general node iteration pattern and paste it in. Right, starting at the top node, right, while the node is not null, right, print out the element followed by a comma and a space, right, and then n equals n next, right, go to the next node, right, and then at the end of the loop, print out the string bottom, right, and that's it. So that's iterating over a linear sequence of nodes. Okay, that node structure that I showed you. Here, right? Every node has an element, but every node also has a pointer to another node. So that's an example of structural recursion. Right? So by structural recursion, I mean the structure of the struct, right, is itself recursive. Right? Every node has a pointer to a node. Right? That node has a pointer to another node. Right? That node has a pointer to another node, and so on, right, until you reach a node whose next link is null. Right? So it's structurally recursive, but it's not infinitely recursive. Right? Eventually, you'll hit a node whose next link is null. Right? If you ever have a recursive structure, and you will see examples of many recursive structures, right, especially in CISC235, it makes it very easy to write recursive algorithms that operate on those structures. Right? Because the structure is itself recursive. Right? So it lends itself naturally to writing recursive algorithms. When you start to work with trees and graphs, you're going to find it way easier to write recursive algorithms that do something on the tree or graph than it will be to write an iterative version of the algorithm. Right? For the iterative version of the algorithms, you have to introduce extra data structures. Right? So, for example, if you want to iterate non-recursively over the nodes of a tree, typically you use a stack or a queue. Okay, so let's look at this print function. Right? I want to take this print function, and instead of using iteration, I'm going to use recursion. Right? So here's here's print. Right? I'm going to print this stack. So I'm going to start by printing out the string top. I'm going to end by printing out the string bottom. Right? In between, I'm going to let a recursive helper method deal with printing out the individual nodes. Right? So print REC, that's the recursive implementation of print. Right? I'm going to start by calling the function using the top node of the stack. Right? So here's the recursive implementation. Right? So the print recursive will print out that node n and all of the succeeding nodes. Right? So that's the job of this function. All right. So what is I'm going to skip the base case for now. What does the recursive case look like? Right? So this is supposed to print out the node n and every node after it. So I'm going to print out the node n. Right? So print out the element that's sitting in the node, right? Followed by a comma and a space. Right? Now I want to print every element after n. Right? So how do I do that? Well, I just call the recursive method again. Right? This time passing in the next node in the sequence. Right? So what does that do? That's going to print out every element in the sequence starting at the next node. Right? So you come back up to here. What does this do? Well, it prints out that node, and then it prints out all the other elements starting at the next node, right? And so on and so on and so on. Right? Eventually, you reach a point where n is null. Right? So eventually, n.next will be null when you hit the last node in the sequence. Right? So when that happens, you're done. You just return. Right? And that recursive function there will print out all of the elements of the stack. Right? Okay. Any questions about that, about the recursive function? Anybody? How about iterating over the nodes of a sequence? Anyone? Okay. And how about push and pop? We're all okay with that? No questions? All right. That's it for today. See you on Wednesday. Your midterm, something funny happened with the marking on the midterm. One of the TAs looked at some of the midterms, but didn't mark them. But when you look at a midterm on OnQ, it automatically saves it as a draft, so it looks like it's been marked. So when I went to look at them all, a bunch of you got like 5 out of 100. And I was like, well, that's not good.